Welcome to Dove Biology APES Lessons to Go. This is Unit 2, Science Systems, Matter and Energy, an Introduction to Systems. It is the understatement of the year to say that Earth is a complex system. We define a system as a series of components that both function and interact in some regular and theoretically predictable manner, and can be isolated for the purposes of observation and study. To be able to understand a system, we can create models in which we can observe and predict inputs that are going into our system, throughputs, things that are going through our system, and then outputs, things that are coming out of our system. If we imagine the Earth as a system as it is, we know that one thing that definitely comes in is energy. Energy comes in from the sun in the form of light and heat. That energy is collected by plants through the process of photosynthesis and stored in carbohydrates, which are then released by the plants themselves and consumers. As those organisms metabolize, they generate heat, and that heat radiates out into the atmosphere and eventually back out into space. So we say that the Earth is an open system for energy because energy comes in, goes through, and comes out. Now, in terms of matter, all of the matter that ever is and that ever will be on planet Earth is pretty much here. While indeed there are a few items that are added from extraterrestrial sources, meteors, etc., and when we send things into outer space and they get left out there, that space debris, there's a little bit of matter that leaves, but overall, the matter that is here is all that we really have, and so we say that the Earth is open system for energy, but closed for matter. Now, systems respond to changes using feedback loops. In a feedback loop, a system's outputs of matter, energy, or information is going to create a feedback loop that's going to instruct the system to either do more of what it was previously doing or to do less, to either amplify the change or to try to correct that change and go back to our normal set point. There are two types of feedback loops. The first one that we'll talk about is a positive feedback loop. Positive feedback loops will amplify a change, and typically they move a system away from its equilibrium state. An example is with vanishing Arctic ice. As temperature rises, the Earth is changing from its set point. It's moving from an optimal temperature to an increased temperature. That increased temperature may cause Arctic ice to melt. Arctic ice has a high albedo. It reflects a lot of the sun's energy. But when it melts, we have darker ocean water that is present, which has a much lower albedo, and so it absorbs more heat. If more heat is being absorbed, we're actually going to see an increase in temperature. We're actually amplifying that initial change of a temperature change. So then, with that increase in temperature, we have more ice melting, which means we're going to have more heat absorbed, which means the temperature is going to continue to rise. So as this positive feedback loop continues, we're going to be amplifying that initial change. On the opposite side of that, we have our negative feedback loop. Negative feedback loops are corrective loops. They tend to dampen or buffer changes and try to hold a system to some equilibrium state. For example, that same warming may cause an increase in evaporation. Increased evaporation may lead to the formation of clouds. When clouds form in the right location, they actually can reflect the solar energy away from the Earth and reduce the temperature to try to bring it back to the set point. So while we had an increase in temperature, a negative feedback loop tries to correct and bring things back down to the set point. One problem with complex systems is they oftentimes show time delays between the input of a stimulus and the response to it. Time delays allow a problem to build up slowly until it reaches a threshold level and then causes a major change in how that system behaves. If the delay is too long, it might mean that a corrective action might come too late. A good example of this might be chlorofluorocarbons in our ozone layer. CFCs were produced as a component of refrigerants and propellants. Down here in the troposphere, they're very non-reactive, and so they were thought to be a perfect chemical for their usage. But as they rose up into the stratosphere, they would be interacting with ozone, breaking it down, which then created this hole in our ozone layer. It took a long time before we were able to realize that this was happening and institute corrective actions, like the reduction and eventual elimination of CFC emanating products. Another thing with complex systems is oftentimes processes and feedbacks can interact together to amplify the change. We call this synergy. An example of this would be with smoking and asbestos. With smoking, if you smoke, you have a chance at cancer. If you are exposed to asbestos, you have a chance at cancer. But if you smoke and you have an exposure to asbestos, you have an even increased chance of cancer. Synergy can amplify the action of a positive feedback loop. It might be able to promote positive changes, but it can certainly also promote negative ones. If we study systems closely enough, we can identify those potential synergistic interactions so that perhaps we can prevent the ones that would be negative and promote beneficial ones. Later in class, you're going to be asked to make some models of systems. With these models, you'll be able to explore different interactions and see how both positive feedback loops and negative feedback loops work within that particular system.